of the ground, you go away from the transmitter. Instead of receiving this kind of signal, you receive something like that. And those oscillations are due to, obviously, to this sin squared, this term here, because this is constant. This is constant, okay, you have this square, so this would be this line. And on top of that, you have this term. And this term fluctuates quite quickly. Now, what is the problem? Why does it fluctuate? It fluctuates because in a certain point, the two electromagnetic waves are perfectly in phase. So they sum up. In other points, they are opposite in phase. So they cancel, or tend to cancel each other. And everything depends on the difference in phase due to the difference of path length. The trouble is, when they sum up, the received power doubles with respect to free space. Those are 3 dB, roughly. But when they tend to cancel each other, the resulting field will be much, much lower than the free space. We're talking dB here, so if you take this difference, this distance, this is 10, 20, 30 dB. This signal, with respect to this one, is 30 dB weaker. 30 dB means 1,000, a factor 1,000. And the things keep oscillating like this, and all of a sudden something happens at this breakpoint here. And now we shall discuss what happens beyond the breakpoint. Question so far, is it clear what is happening here with respect to free space? Free space would be perfect, but it does not exist on this planet, unless you are very high with respect to the Earth. What happens here? Because at this point on, things change abruptly. We still have to go back to the mathematics to understand what is happening. Trust me, if you go and do some measurements on the ground, this is exactly the pattern that you find. This is not theory. This is not only theory. This is something that you will experience or feel if you do measurements. Now, at a certain point, when D increases beyond a given point, what happens? Happens that this number here, since those terms are constant and D is getting bigger and bigger, these terms become very small. And you remember that sen squared of x is almost equal to x squared if x is very small. So at a certain point, you can approximate this equation by its argument. Don't let me rewrite it, but you can rewrite it. over a certain point that is called the breakpoint, and I give you then the value, the exact value, this equation can be approximated like follows. And all of the magic, you find out that this cancels with this. Few terms cancel out. And you end up with this expression. The receiving power is the transmitted power, gain of the transmitter, gain of the receiver, HT, HR divided D square. This is what you get if you simplify the terms that appear here. You have 4p squared, they cancel out with this, etc. It's very simple. You can do it yourself. And what is striking in this equation? You can spot it. There are two things, at least, that are very, very strange in that equation. First of all, the power decreases with distance. Which power? While in free space, it increases with the d squared. So, at a given point, the received power decreases with distance much quicker than you would expect in free space. In free space, you would expect something like that. But beyond this point, it stops fluctuating. There is no fluctuation anymore. And the power is reduced like 1 over d to the 4th power. While here it is going down with 1 over d squared. First weird thing. So, in this situation, for this geometry, the breakpoint where this happens is written there. The breakpoint is a distance that is for HT HR divided by lambda. For this geometry at 900 megahertz, the breakpoint is slightly over 200 meters. We are not talking of kilometers. We are talking, those are 100 meters, this may be 200 meters. So after that distance, your receiving power drops much more quickly than in free space. And you don't understand why, unless you have worked out the mathematics of this. And then there is another striking thing that this is more tricky to point out in this equation. There is no dependence on frequency anymore. There is no dependence on wavelength. In free space, you have a dependence on wavelength. Lambda is in the equation. Here, it does not appear anymore. So the insertion of the power received does not depend on wavelength. Questions so far? Yes.
How do you calculate the breakpoint?
Are you? I will determine the breakpoint. When you stop oscillating from this. is if you draw this function, sin squared of that function, at a certain point it stops oscillating. It depends on the wavelength. Because the argument tends to become very small. So it's quite large for small values of d. So it keeps on doing many circles of phase, and then it becomes slower and slower, and then it stops. Does not go to zero anymore. Other questions? Okay, that was flat surface. What happens if the surface is not flat? We move to the next. Okay, let me remind you that starting tomorrow we start doing exercises, so please bring your calculator or your computer, whatever. Okay. Piece of paper, pen. Okay. Now roughness. What happens is our surface is not smooth. Surface is not smooth, then in principle a specular, perfectly specular reflection is not possible. We have the so-called diffuse reflection. What the mechanism is simple to understand. If you have a situation like this, and you have, so this is the profile of the reflecting surface, and you have an incident wave that is incident like this. Then, as you can imagine, each portion of that surface will scatter, will reflect the energy in a different direction. So this will reflect here, this will reflect there, this will retro-reflect, etc. So the reflection will be not specular, but the energy will be scattered in all directions. So this is not a black and white process. That is, the transition from the specular reflection to the diffuse reflection is smooth. It's progressive. So we can go from a perfectly specular reflection to a completely diffuse reflection and everything in between. Now, smooth or rough? On what does it depend? It depends obviously on the surface and on the wavelength of the incident wave. Okay, let's start with, to understand this, let's start with a very unrealistic situation. Where you have a surface like this. This is very unrealistic, but this helps us in understanding what's going on. Okay, let's consider 2 points. Point here, where we have an incident electromagnetic ray that is reflected. And then a point there where the same thing happens for another electromagnetic ray. Okay, and then now let us consider now 2 transverse planes, where this is point A, this is point B first, so this is point B, this is B first, and then we take other 2 points that are C and C first. Okay, now the geometry is very simple, so simple to be, as I said, unrealistic. But you can see that this part, the part A, B, C, will be longer than A first, B first, C first. So A, B, C, longer. Now we calculate, I will give you an expression of this difference in length. And a criteria to say if that surface is rough or not is based on the difference in length between those 2 parts. Because the difference in length translates into a difference in phase. So let's call this B. Now, the mathematics and we say AB plus BC, this is this part, minus and this is the other part, the difference, and we call this difference delta length. It can be, we said all the trigonometric equation, but it's d divided by sinus of c, when c as usual is the incident angle. Obviously they are all the same for this geometry. Times 1 minus and if you remember that this thing is the sinus of alpha angle, we have seen this expression before when we were talking about difference of path length. This is 2. Okay, difference in length, and now phase difference. As usual, the difference in phase is equal to the propagation constant times the difference in path length, that is 2 medium divided by lambda. And this is the phase difference. Now, to decide if a surface is smooth or rough, the Rayleigh criterion Rayleigh, you will find a lot of works on electromagnetics by Lord Rayleigh. It was the first to explain, for example, why the sky is blue. The Rayleigh criterion states that if delta theta is greater or equal to 90 degrees, then the surface is rough. If the difference in phase between those two electromagnetic rays exceeds 90 degrees, then the surface is rough. And this can be theoretically justified, we don't do that, but it can be theoretically justified by remembering that if the phase difference tends to be bigger, those contributions tend to cancel each other because they start to be opposite in phase. So there will be no radiation or very weak radiation in this direction. So there will be no specular refraction. but we do not demonstrate that. We just state the relative period. So, for this particular geometry, this condition, if you put this condition in here, the surface is rough, is the dimension of the irregularity E is greater than lambda divided 8 sine C. So you see that the roughness depends not only on the dimension but also on the wavelength and on the angle of incidence. So the same surface can appear smooth or rough depending on the frequency. And for a given frequency, it can be smooth or rough depending on the incident angle. The higher the incident angle, the more likely that the surface appears as rough. You have all experienced this, I think, several times or a lot of times in your life, this phenomenon. No idea? When you drive your car on the highway, or and I think it happens here as well. When you look at distance, in the distance, does not the asphalt look wet? Yes, it's not wet. It's just a specular reflection. And it is specular reflection because the angle, see, is very small. When you look further closer to you, the asphalt is the same. But then the angle changes. And the reflection from that surface is not specular anymore. And it doesn't look wet because the energy is scattered in all directions. The same happens for radio frequencies. You go from perfectly specular reflection to perfectly diffuse reflection, depending also on the geometry. Okay, this is not a real scenario. Now before the break, let me just be more realistic with a real, what we do with a real profile of a rough surface or smooth surface. Questions so far? Okay, after the break. Communication problems. Okay, we take the break and we go on.
Bien.
¿Qué se juega con las manos? La cachonda. Pero poner la cintura lo que también es.
que hay conexión, hay igual, hay un país que como el